This conference will now be recorded.
Yeah. So in the last class, we were discussing something on like what is the frames, bandwidth, and all the things, right? So we know now like what is bands. There are different bands. Okay, we have different bands. We have bandwidth. So we have frame. You know what is SFN? You know what is SF? You know what is a time slot? You know what is an OFDMA symbol? And you know what is RP? You know what is an RE? You know what is total bandwidth? You know what is a subcarrier? Okay, so these are all things we have seen in the last class, right? Bands, bandwidths, frame, SFN, SF, time slot, FDMA symbol, resource blocks, resource elements, total bandwidth, subcarriers, all these things is what we have seen. Apart from this, we also have okay, apart from this, we also have something from the perspective of okay. So apart from this, we also have something from the perspective of so what I can say is we have seen something on OFDMA, right? We know what is OFDMA exactly, and we know what is SCFDMA. What is the major difference between them? The major difference between them is very simple. This is used, okay, multiple subcarriers are multiplexed. It uses a single carrier. So it saves UE battery, sorry, high battery is used here, low battery power is used here, or low power. So in other words, R is low and power is high. All these things we have seen, okay, so but at the end we have seen the difference between OFDM and SCFDM. So after this we have seen how exactly or what exactly we have with respect what exactly we have we are actually discussing something on the modulation. So we also seen that in the modulation part. Okay, so basically we have uplink and downlink. So in downlink we are using 256 QAM, 64 QAM, 16 QAM, and QPSK. In uplink we are using 64 QAM, quadrature amplitude modulation, and 16 QAM, quadrature amplitude modulation, and QPSK. Okay, so these are the modulation techniques what we are using. So this is for UL uplink and this is for DL. So we have an uplink and we have a downlink modulation techniques. So now what I have is okay. So we have an uplink and we have a downlink modulation techniques. So apart from this, we also seen that if we are using 256 PAM, we have a very high throughput. Right, and we also seen that this we use only whenever the channel conditions are good, right? Already told this also. So this, whenever you're using this, so you will get a low throughput. Throughput is nothing but speed, and your channel conditions are bad. Okay, your channel conditions are bad. So in QPSK it is a low throughput. In 256 gram it is a high throughput. So in the same way, we have 64 QAM, quadration amplitude modulation in QPSK. So when I take a QPSK, okay, so in QPSK again we have a low throughput in uplink and 64 grams. We have a 9. So this is what we have seen. Okay, so we'll further discuss more on this modulation and we'll just go on to the MIMO part. So whenever I say quadrature amplitude modulation, so first of all you should know what is PSK. Okay, so whenever I say modulation, whenever I use a word modulation, basically, okay, so if this is a mobile internal signals are low frequency signals. So this mobile cannot, if I transmit low frequency signal, there will be losses. For example, this is the actual signal of the mobile inside the mobile. But if I transfer the signal at such a low frequency, so nowadays everything is digital, right? So I'll draw a digital signal, okay, instead of an analog signal. Okay, so what I have is actually basically I have a very slow or low frequency bits. Okay, so I have 1 0 1 0 1 1 0. Okay, very low frequency. So if I transmit at such a slow frequency, what will happen is there will be losses. So for that reason, I am trying to mix this with a very high frequency signal. Okay, so with a very high frequency signal. So this now what will happen is, okay. So for example, so now the data 1 0 goes, okay. So for example, if I implement PSK, phase shift keying, so in phase shift keying, okay, whenever it is 1, so it will be like this only. Okay, so now when it is 1 is converted to 0, when 1 dip to 0, so this phase means the direction. Okay, instead of going this way, it will stop going that way and it will go in this order. For whole 0 it will remain like this. Again from 0 it is lifting to 1. Okay, so instead of going in this direction, okay, it will change its phase. So now by this, okay, the receiver will actually, okay, even though actually this and this now will be same. Okay, I mean to say what will happen is now the receiver being an E0 P or a UE, okay, what it will understand that yes, if this is the first part is 1, okay, so here there is a phase shift. So after phase shift it will be a reverse thing. So this part will be definitely 0. Again here there is a phase shift. After this something it is, okay, it is means after this again we have 1. Okay, something like that. If there is a phase shift, definitely it will think that it is a zeros and 1. Again it is a 0. So I'll again a shift. Okay, so again 0. So it is a 0. So here the problem is again here we have a continuous 1. Okay, so for long period if it is 1, it will consider that it is 2 ones. Okay, there is no phase shift. Okay, continuously 1 and 1. So this representation ultimately, okay, by doing this representation, ultimately what we are doing is we are having two important things. One is anyways we are trying to explain the other base station of the receiver saying that yeah, I'm transmitting this data to you, you understand, yes, this is what is the data. Now, okay, so the other major benefit is, so what, so this was very slow, right? Okay, means the frequency was very low in this normal signal. The major benefit was, okay, it is now moving at a very high frequency. So ultimately what will happen is very low losses will take place in this segment. Okay, so ultimately what I can say is this is called as a baseband segment. This is called as a baseband signal. Okay, so baseband signal means even, okay, even your protocol stack, right? Okay, so sometimes there will be a question in the interview. Okay, so your NAS, RLC, PDCP, RRC. Okay, so I'm just sorry, RRC is here, right? So RRC, okay, RLC, MAC, Phi, all these things will come under baseband only. All of them are called as what? They're called as baseband. Okay, so for example, I get lot of issues, lot of tickets. Okay, so in the ticket will be clearly mentioned that the issue is with the baseband. The issue is with the baseband means issue is with this part. Okay, so on this, on top of this, the last unit, what is it? RF. I already explained you. Okay, the last unit is RF unit. So this baseband signal will be taken by the RF, and RF will convert it into a very high frequency signal. This modulation and all those things are done at RF, and RF will transmit. Get the point? RF will try to transmit the signal. So this is still called as baseband. Baseband means here or everywhere the processing is done at a very low speed, because our processors are not capable to process the data at such a high speed as of the frequency. Okay, so if I try to transmit the signal of my processor speed into the air, so your signal will be lost. So what you have to do is, so you have to mix it with the high frequency RF carrier. Okay, this mixing is called as modulation. So this signal is called as baseband, and this is called as a carrier. Okay, this is a carrier and this is a baseband signal. So what we are trying to do is, okay, actually this signal has been generated by a protocol stack. Okay, because this is called as baseband. So now ultimately this signal you are merging out into the signal which is generated from the RF. Okay, so that is nothing but a carrier. So now ultimately this is the output from your antenna, which is called as a modulated signal. Okay, which is called as a modulated signal. So this is the modulated signal what you will get as the output. So now the data will go like this. So this modulation plays a very vital role. Okay, why a very vital role is, okay, so this modulation plays a very vital role. The question is why is a very vital role is because, okay, because based on this modulation how much amount of data is being carried is decided. Okay, based on this modulation how much data is being carried is decided. So instead of one cycle means if I take one cycle, okay, it starts from 0. So 90 degrees, 180 degrees, 270 degrees and 360 degrees. This is one cycle, right? 0, 90, 180, 270 and 360 degrees. So this is called as one cycle, right? This is a cycle. So in this one cycle, okay, so this is called as one cycle. So in this one cycle, so this is 0, 90, 180, 270 and 360. This is one thing. So can I represent one cycle in like this also? This I am calling it as 0, 90, 180, 270 back to 360. Both are same, right? So cycle can be represented that way or this way. So basically what the basic concept is, okay, this phase shift will be done, okay, means the phase shift will be done for every 90 degrees. Means for every 90 degrees of your baseband signal there will be a phase shift. Okay, so there will be a phase shift of 90, means for every 90 degrees there will be a phase shift. Okay, that means what I mean to say is actually, okay, actually your data was, okay, actually your data was like this. Okay, 0 and 1 was traveling like this and it was actually taken like this. But now how it is going out is, okay, this zeros and ones. Okay, for example, if I want to transmit 0, 1, okay, 0, 0, 1, 0, 0. Okay, for every 90 degrees there will be a phase shift. Okay, for every 90 degrees there will be a phase shift means, so for example, okay, this is the signal, actually this is the cycle, right? Okay, so now for every 360 degrees there is a phase shift. For example, there is a phase shift for every 360 degrees. Now here what happens is, okay, this is for one cycle. So now basically what happens is there will be a phase shift for every, okay. So now for example this is your baseband signal. Okay, so this is the baseband signal. For this baseband signal, actually it was planned like this. So presuming this is one, this is zero, this is one, zero, and one. Okay, so this was the cycle. Okay, so there was some phase shift at this particular point, right? There was a phase shift at this particular point. After 180 degrees, there was a phase shift. Getting my point? So this is presuming this is 0, this is 180 and this is 360. So at around 180 degrees there is a phase shift, right? So again I come here at this particular point, again I have a phase shift, right? Now this phase shifting we have reduced to till this particular point only. Getting your point means in one voltage only, means for half a cycle, that means for half a cycle we will be having a phase shift now. So that means for half part of this one, okay. So now, so my phase was like this, okay. Only for this half part, for 90 degrees only, okay. Just a second, no? Just give me a second. So, anyways, the conclusion or the thing what I want to tell or what I want to discuss is the point over here is okay. The overall point over here is I want to tell us okay. We have okay. So ultimately, what I want to say in a single statement is okay. Ultimately, what I want to say in a single statement is okay. So the phase is shifted for every 90 degrees. That means if I draw, okay, like this, so there is a phase shift over here. In every phase shift, there are some data going on. Okay, what we try to do is, okay, for from 0 to 90 degrees, we have a phase shift. In this phase shift, instead of before we were pumping one bit, now I'll pump two bits of data. Okay, so from 90 to 180 degrees, I'll pump two more bits of data. From 180 to 360, I'll pump two more bits of data. Okay, here two more bits of data. Okay, so that means what I mean to say is for every, okay, this quadrature phase, this is called as quadrature phase shift key. QPSK. So QPSK is nothing but it's an improved format. Quadrature mean the meaning of quadrature is okay 4 times phase shift keying. So quadrature means 4 times phase shift keying. Quadrature phase shift keying. So 4 times phase shift keying means so here we have one phase shift 0 to 90 is one phase shift. So that means in a cycle 0 to 90 is one phase shift. This particular point we have one phase shift. The signal will go from 90 to 180 is one phase shift, and 180 to 360 is one phase shift, and sorry 270 to 360 means in one cycle we have four phase shifts. So now what happens is for every phase shift, okay, two bits will be transferred. Two bits will be transferred. So you don't have to remember all the story. Okay, so the story is very simple. What I want to say is okay. So QPSK is a modulation technique. Okay, QPSK is a modulation technique. Okay, QPSK is a modulation technique where where phase shift okay phase shift is done 4 times in one cycle. So for every phase shift, okay, one symbol is transferred. One symbol is transferred. So this is not the OFDMA symbol. This is a different symbol. One modulation symbol is transferred.
So one symbol is equal to 2 bits.
Okay. So this is how the story is. QPSK is a modulation technique. It's a modulation technique where phase shift is done 4 times in one cycle. Okay. So that means in one cycle 4 times the phase shift is done in this one cycle. So now for every phase shift. So I'll try to represent means the cyclic representation is very tough and nobody represents in this way actually. Actual representation nowadays is we are doing this. So this is one cycle 0 to 90, 90 to 180, 180 to 270 and 270 to 360. This is one cycle. So for 0 to 90 we transfer one symbol. So 90 to 180 one symbol and 180 to 270 one symbol and 270 to 360 is one symbol. So this is called as one symbol. Okay, modulation. So now, okay, so QPSK is also 4 times phase shifting, 4 times phase shift keying. 16 QAM is also 4 times phase shift keying. 64 QAM is also 4 times phase shift keying. And 256 QAM is also 4 times phase shift keying. Means, okay, in all are 4 times phase shift keying. That means what I mean to say is, so what I mean to say is, so I have this is for QPSK. So in QPSK also the cycle is 360 degrees and it is shifted 4 times. And 16 QAM also it is same. Okay, 64 QAM also it is same. 256 QAM also it is same. Now the question is, what is the difference then? So whenever I say a phase shift, okay, whenever I say a phase shift, okay, that phase shift is done, okay, basically from LTE language. Okay, so the bandwidth what we have, okay, the bandwidth what we use it is only 15 kilohertz of carrier. So internally it is actually 15 kilohertz of carrier. Okay, whatever it is. So in that given bandwidth, okay. So what happens is, okay. So for example, what I can say is bandwidth means there has some space. Okay, in that phase, okay, in that space of bandwidth, okay, what I'm trying to do is I'm shifting the phase of the carrier and I'm just transmitting. So now for one phase shift there is some bandwidth. In that particular bandwidth, okay, in that particular given bandwidth, okay, so I can have two dots. I can have two dots. Okay, so these two dots represents, okay, one symbol. These two dots will represent one symbol. So for every phase shift, I have two dots. So now the question is, why only 2 points in a given bandwidth? We can have a little bit more dots, right? We can point out 4 dots instead of 2 dots. Yes, you can point out 4 dots. Okay, you can point out 4 dots. Now again, somebody asked me why only 4. You can only point. You can make it 6 also, right? Means in a given bandwidth of that particular phase, I can have 6 locations I can mark. Okay, I can adjust my data. So somebody asks me, okay, why only 6? You can make it 8 dots. You can make it 8 dots, right? So now, okay, now the problem here is, okay, here we have 2 dots, 4 dots, okay, 6 dots, okay, here we have 2, we have 4, here we have 6, here we have 8. Okay, now for example, there are some losses. Whenever there are losses, what will happen is there will be some disturbance in these dots. Means this will be out of its phase. Means it will be out of its position. So at that particular point, what will happen is this dot while traveling. Okay, so this is the bandwidth and this is the base station. So from this base station to the mobile, okay, these dots are going in a bandwidth. So once they are coming in a bandwidth, there are some losses. Because of these losses, what will happen is, okay, so transmitter had transmitted your this dot somewhere here, okay, but while receiving it moved somewhere here, somewhere here. Okay, dots were somewhere here, but in the given region only. It moved somewhere there, it moved somewhere here. Okay. So there was some phase shift. Little phase shifts will be there because of this interference and losses. Okay. So now what will happen is, okay, the receiver will be able to receive. Okay. So now the mobile's receiver sensitivity, what we call it as, receiver will search this whole region of that particular bandwidth, and this will say that maybe this dot is this dot only and this dot is this dot only, and it will be able to decode your data very easily. Getting my point? You will be able to decode the data very easily. So now you take this second case. In the second case, what happens is little high losses were there. So this dot has moved little bit here, and this dot has also moved little bit here, and this moved somewhere here, and this moved somewhere here. So now what will happen is, okay, so if it would have been only two dots, okay, this moves somewhere, but because of four dots, the map means the space is very low. Okay, in a room, if the space is very low, there is a problem of mixture. So this got mixed up. So as because of very high fluctuation, there was a mixture. Now, can the receiver detect which dot is what? It is very difficult because, okay, receiver will not understand here which bit is what, which note is what. It will not be able to do. So at this particular case, what will happen is there will be a decoding error, or we call it a CRC error. Cyclic redundancy check is failed because of you will not be able to, the receiver will not be able to detect or decode the bits properly. Okay, so decoding error. So you will not be able to decode properly. So now what will happen is, okay, so imagine for 4 bits only you are saying like that. If it is a 6 bits, the chances is very difficult, because what will happen is if there is a high interference, okay, so the mixture is so much you will not be able to understand, the receiver will not be able to understand which bit is where. So it will be again a decoding problem for the receiver. So you tell me in the 8-bit case, okay, so in the 8-bit case, in the given bandwidth, there will be a huge movement, because the bits will not stay at its place, because you are not transmitting somewhere, you are transmitting in some photons. So it will be a moving part. So it will be very, very difficult for the decoder to decode this 256. So this is the problem. The problem is decoding 256 QAM signal is very tough. Signal is very difficult. So decoding 256 QAM signal is very difficult. So it is something like what I can say is, okay, like I have 4 cars. Okay, I have 4 cars. So one is normal Maruti 800, one is a Ferrari car, and one is normal you can say Honda City, and one is Mercedes Benz. So now I am saying, okay, so what I'm trying to say is I'm trying to ride the Ferrari in some streets of you can say, if I give an example, if you're riding say in some village, or if you're riding in some small streets, okay, so in Amirpet streets or in Charminar streets or somewhere, okay, a Ferrari car with a 250 kilometers per hour, what will happen to that car? Will car be able to go? Okay, so you are saying that I am driving Ferrari car. Okay, but will you be able to drive that car? You will not be able to drive that car, right? So now, what is the condition for driving the Ferrari car? What is the condition? The road should be very clear. There should be no one on the road. It should be a very big road. If highway is there, that's what. So for adopting 256 modulation, okay, between the base station and the node B, okay, there should not be any losses. The path should be very clear. If it is a very clear path, then there will be no phase shifts in the bits, whatever you are transferring, and there will be no mixing. So now the receiver will be able to easily decode it. Getting my point? You will be able to easily decode the data. So now that is what is the major problem we are having, the RF part. Getting my point? This is the actual main concept in this. Because what happens, radio conditions are bad. Okay, means road is very bad. Will you decide? Will you go in a Ferrari car or a Maruti 800 or a small Swift car? So definitely you will not prefer a Ferrari or a very big car, right? You will not prefer a very big Volvo bus or a car, a big car. What is there? Yeah, roads are bad. So what I'll prefer? I'll prefer for a small car. Even though two people are going, no problem. I will go with a small car. If road is very nice, definitely I'll take a very big car. I'll take my family, everybody with me. So same concept here also. The concept is, okay, if this road is very clear, okay, I will go in a Ferrari. Now you tell me if road is bad. If road is bad means you have high losses. Your radio conditions are very bad, high losses. When you have a very high losses, will you go in a Ferrari car, 256 km? So if you go, presuming you go, what will happen? Your main concept will only go. That means your receiver will not be able to decode the data only. Ultimately, you will not receive any data. So what you have to do? Ultimately, you have to shift your car to QPSK, because in QPSK it's manageable. Yes, only 2 bits are there. If there is some phase shift also, your receiver will be able to decode it. So that is the main concept. That is the main reason. Okay, a lot of people ask this common question in the interview. Okay, I think many people don't have an answer for this. Okay, but the concept is very clear. What I want to say is, okay, the concept is very clear. Is okay. So that means, see here. Okay, it's a very clear concept. That's what I told you in the starting. So E node B. Okay, so ultimately, which is a very good one. Ferrari is good. It is taking a lot of people. It is carrying high amount of data. But we have a condition for it. What is the condition? Radio condition should be good. Okay, so I ultimately my destination is to get high throughput. But how can I get a high throughput if I don't have a good radio condition? If I don't have a good radio condition, still I'm trying to pump 6 bits. What will happen? There will be some phase shifts and mixing, and you'll not be able to decode. Ultimately, your decoding failure will happen, and you'll not receive any data. So, for that reason, okay, so what we say is, we are transferring how many bits in QPSK? 2 bits we say it. How many bits? 2 bits. Whenever you are using QPSK, we transmit 2 bits. When you are using 64, 16 QAM, we transfer how many bits? 4 bits. Okay, so whenever you are transmitting 64 QAM, how many bits you transmit? 6 bits. You are transmitting 256 QAM, how many bits? 8 bits. Okay, even though we have the concept of 8 bits, okay, what is the condition? The radio condition should be very, very. So now you tell me where the throughput will be high. Throughput will be good when you use this. But the condition is, radio condition should be good. So now, how base station knows that the road is clear? Because E node B is anyways doing some modulation and is pumping. How E node B will know that the road is very clear? Because E node B is only one way it is doing and transmitting it. So mobile will every time will send a report to E node B saying that this is what is the channel conditions. That report is called as a CQI report. So after release time, this is called as a CSI report. So in CSI, CQI is present. Channel state indicator. So in CSI, there will be CQI. Okay. Channel state indicator. So inside CSI, we will get a CQI. Okay. So mobile will tell to the E node B, this is what is the radio conditions are there. Now based on those radio conditions feedback, this is the feedback. Feedback of losses. How many losses are there? So feedback of the losses will be intimated by the UE to the E node B. Now based on that feedback, what E node B has to do? So now you tell me if radio is good, radio conditions are good, means losses are less. If radio conditions are good, so what will be the modulation technique? You tell me. It will be definitely 256 QAM, because how many bits we are transmitting? 8 bits. If they are very good radio conditions, then I'll use this. Now you tell me, can you use same 256 QAM when I have a bad radio conditions? On bad road, can I use a Ferrari car? What will happen? You cannot go only, right? So in bad radio conditions, so what I'll do, I'll use only QPSK. So how many bits? 2 bits. Getting a point? So I use 2 bits. So this is the concept. So ultimately when you are pumping 8 bits, when you are pumping 8 bits every time, when you are pumping 8 bits, so this you say 8 bits per symbol, modulation symbol, this is 2 bits per symbol. So 8 bits you are pumping, ultimately what will happen? Throughput is good. So now you tell me what solution you will give for this problem. Till now nobody has given the solution. This is one of the major concerns which is actually, what you can say, keeping drive test engineers job. So if presuming for bad radio conditions also, we would have got some new technique where we can use 256 QAM and pump 8 bits. There is no need of this DT engineers, because for bad radio conditions also I am getting same throughput, and good radio conditions also I am getting same throughput. So ultimately what happens? Ultimately there is no need of any good or bad radio signal, any radio signal I am getting. So I'm concluding my discussion. The discussion conclusion is something like this. So the conclusion is, you should. I hope you remember all this. The conclusion is in LTE. As I already told you. So on this, I told you this. Only the thing is, in uplink and downlink, UL and DL. In UL we are using 64 QAM. So we are using how many bits? 6 bits. So and 16 QAM and QPSK. In DL 256 QAM. 64 QAM. QPSK. So only condition is this has what? This is basically used either in uplink or downlink. In good radio conditions. So good radio condition means good RSRP, RSRQ, SNR, low blur. These are called as good radio conditions. So when these are good, so ultimately in these good radio conditions, They're using this modulation technique. Ultimately, this will lead to good CQI reporting in uplink. Okay, this is in downlink. In downlink, you could receive this all this. We say that we are receiving good conditions. So here you'll report. This is the report. You'll report a good CQI. So ultimately, this is what you will get an output. Ultimate thing is good throughput. Ultimately, what you'll get? Ultimately, you'll get a. So I take the second case. So in the second case, this is using bad radio. Bad radio means same thing. All these are bad. Okay. So ultimately what you'll get. So this will be a bad CQI reported. These two are same, and you'll get low throughput. Ultimately you'll get it. So this is how we have. I hope you got it. What I'm trying to say. So this is medium throughput. Okay. So good and bad in the medium part is what I told. So this is something with respect to modulation, and this is an NT question. If you remember this right, so that's what based on these things only you can clear your NTUs. You can talk. So when you come at the weekend, I hope you are prepared and you are coming. So you should express like how I am expressing. Means how I am speaking, you should speak like that very fluently. I want fluency in your speech. Okay. So
It will be low SNR for the good radio conditions. Low SNR.
bad SNR. Yeah, low SNR. Or a bad radio conditions. There's a question. Means modulation technique will assign post RF condition verification. It's not pre-configured. Yes, modulation techniques are pre-configured. Maximum value is configured. Okay, so that means, for example, E node B is maximum capability. E node B is maximum only capable of 16 QAM. So now it shifts from QPSK to 16 gram only. There will be a shift between these two. So maximum value is configured, but variability is based on the RF conditions. Okay, there is a configuration and modulation. So what you have to configure? You have to configure the maximum value. So presuming I configure maximum value is 256. So it will not exceed 256. If I configure only 16 gram, it will not exceed 16 gram. So max value you can configure it in the base station. So based on that, base station will say this is the maximum value I can adjust for 256. That is 256. But variability is under radio conditions. It is not constant. So even though if I configure 256 QAM, I don't guarantee that I'll get every time 256 QAM. I can get 64, I can get 16, or I can get QPSK. Okay, but maximum I'm saying that I'll get 256. Okay, so a lot of parameters are like that. There's one more question. Sometime I see that radio conditions were good, SNR was good, modulation was also 64 cam, even I was getting low throughput. What could be the reason? So everything is good, still we are getting a low throughput. Okay, there are a lot of reasons. Okay, so it could not be a modulation reason. The throughput or the dip has happened at the PDCP. PDCP packet discards, or they are discards at RLC, they are discards at MAC layer. Okay, it is not compulsory that every time throughput dip is because of only modulation. Okay, throughput dip can be because of some packet discards at application also. So that discussions we will discuss what all the different reasons for the throughput dip, even though we have a good radio conditions. Okay, but this is the major factor which is affecting at the RF level. So that is not an RF issue, that is a stack issue. So anyways, I'm concluding it. So in tomorrow's discussion, we will discuss with MIMO, multiple input and multiple output. MIMO. Okay. So anyways, thanks for joining. So you have any more queries, you can ping me and I can ask the questions. We'll start little early, little early. Okay, I was late today. So actual plan is I'll post the meeting ID at 8:15 and I'll start the class at 8:30. Okay, this I'll try to maintain as a strict thing because if I start at 8:30, right, we can at least have one hour 15 minutes class. No, it is only 1 hour class. Okay, thank you.